Welcome back. In this web lecture, I'm going to introduce you to the very basics of lever systems. So why are we interested in levers? So if we think through the evolution of tetrapod limbs, if we look at the very earliest tetrapod limbs, the bones were sort of these short, stumpy, globular hunks of bones. They had sort of short, stubby little limbs. But as evolution proceeds through the different groups of tetrapods, what we see is a trend toward these very elongated, slender limbs. And once this happens, then the limbs can effectively be used as lever systems to manipulate the properties of those limbs. Let's look at the basics of a very simple lever. So first of all, let's think about the different components. So a lever is defined as a rigid strut that transmits a rotational force through a fulcrum, or a center of rotation. So this is our fulcrum of our very simple lever system, and we're going to apply a force, and that force is going to be transmitted through this lever through a rotation to the other end of the lever. So the distance from the center of rotation to the application of force is known as the lever arm. So we can define a lever arm as the distance from the point of rotation, so from this fulcrum, perpendicular to the direction of the application of the force. So if the force is being applied straight down and this board, this lever is flat, the lever arm is just going to be the distance from the center of rotation straight along this lever to the application of the force. And if this force is unopposed, that's going to cause a rotation in this lever. So when we rotate this changes the properties of that lever arm. So remember, it's the perpendicular distance to the application of the force. So we need to make sure that we're measuring our lever arm perpendicular to this line of force. If we extend that force with a dashed line, this would be our line of force. So now we've got a lever arm that is a little bit less than just the straight distance along the lever from the center of rotation to the application of the force. It's going to be a little bit smaller, and we can compute mathematically what this would be using simple trigonometry. If theta is the angle between the lever and this line perpendicular to the direction of the force, and then d is just the straight distance along the lever from the point of application of the force to the fulcrum. We can just use the cosine of this angle. D is the hypotenuse of our right triangle. The right angle is here between the lever arm and the direction of force. And so we've got adjacent over hypotenuse. If you remember your trigonometry, L over D is going to be the cosine of theta, so the lever arm is going to be D cosine theta. Remember, cosine theta is always less than 1, so this lever arm is always going to be a little bit less than that distance if there's any angle here. So this application of force along a lever arm through a pivot is known as a moment. So the moment is the rotational force around the pivot point. It's the force that's experienced here that's causing this rotation. And we quantify the moment as the magnitude of the force, this linear force that's applied to the end, times that lever arm. So it's force times the lever arm. If we have this input force that we're applying and an input lever, if this force is unopposed, that's going to cause a rotation in this lever around its pivot point. If, however, we oppose this input force with an output force of some kind, we want to actually balance this force and keep the system from moving. So now we've got an output force in the form of this weight that we've put on the other end of our lever system. And that's also going to have associated with it a lever arm, a perpendicular distance between that output force and the center of rotation of the fulcrum. So we can call that our out lever arm. And so when the moments generated by each of these forces are equal, then there's going to be no movement in this system. So whenever the system isn't moving, that means that the input moment is going to be equal to the output moment. And by our definition of moments, that also means that the in force times the in lever is going to be equal to the out force times the out lever. So this is the system in equilibrium where there's no motion. Whenever this is not completely balanced, the moments are not equal, then there's going to be a physical movement, a rotation. So now let's move our fulcrum and make it so that our input lever and our output lever are not equal lengths. In this situation where they were equal lengths, the input force is going to be able to balance an output force of exactly equal magnitude. If L in equals L out, then force in has to equal force out. So it's going to get as much force output out as it put in this system with equal leverage. So now what we've done is we've made the leverage unequal on the two sides of the fulcrum. So let's say we have the same input force and we want to see how much weight we can balance on the other side. So now we've got a much longer in lever than out lever. We've doubled the size of the in lever relative to the out lever. So it turns out that that means that we can double the amount of force that we can balance with this system in equilibrium. Why? Because if the input lever is twice as big as the output lever, that means the output force is going to have to be double the input force to keep this system in equilibrium. So doubling the length of the in lever doubles the amount of out force you can generate with this lever system. And we call this being at a mechanical advantage. You get more force out than you put in because of this lever system. And this is the typical use of levers that we always think of. If we use leverage to lift a heavy object, this is what we're doing. We're using a very large input lever, a relatively short output lever to gain a mechanical advantage and be able to lift heavy weights. If we move the fulcrum in the other direction now, so now our output lever is twice as long as our input lever. Now for the same amount of force input, now we can only lift half as much weight or balance half as much weight on the other side. A shorter lever means that you get less force out than you put in. You're having to put in twice as much force to lift the same amount of weight is another way of putting that. In this case, you'd be at a mechanical disadvantage. You get less force out than you put in. But you're at a mechanical disadvantage. But if you think about this system in motion, so let's go ahead and not balance that force, let the lever move. Now, the out lever moves a farther distance than the in lever moved in the same amount of time. This is all an interconnected system, and so when this moves, you get a relatively large deflection on the output side, a relatively short deflection on the input side in the same amount of time. What does that mean? That means that this end went faster than you moved it at this side. And now what you have is a velocity advantage associated with that mechanical disadvantage. So we see in lever systems a fundamental trade-off between force and velocity. And we can quantify this trade-off in a quantity known as gear ratio. And the gear ratio is equal to the length of the out lever divided by the length of the in lever. So remember, all of this mechanical advantage, mechanical disadvantage depends only on the relative lengths of the out lever and the in lever. So we can see that in low gear, if this quantity L out divided by L in is less than 1, that means that the input lever is longer than the output lever. Then we have a mechanical advantage. We're going to have relatively high force output, low velocity on the output side, and a relatively long in lever. All of these associated with having a low gear ratio. So you can think of this as being the low gear on your bicycle, right? You get a relatively large amount of force output for the amount of force you put in, but you don't get a whole lot of speed out of it when you're in low gear. You're turning your pedals relatively fast to get a relatively small advantage in speed. For high gear ratio, this means that there's a mechanical disadvantage. So if you're at a mechanical disadvantage, your output lever is longer than your input lever. So you're going to get a relatively low force output, but a relatively high velocity output. So this is going to be associated with a long out lever. This is also directly analogous with high gear on your bicycle. You don't have to pedal your feet quite as fast to get more speed out of it, but you don't want to use that going up a hill because you're not going to get a lot of force output in high gear on your bicycle. So we're going to employ these ideas to think about the design of different kinds of vertebrates that are adapted for different functions in terms of this gear ratio and the relative lengths of input and output levers. And I'm just giving you sort of a preview glimpse of this now. We're going to work on this in great detail. But what you see here is that there are big differences in the relative lengths of these input and output levers in these two different skeletons you're seeing that are adapted for very different functions. So this is what we're going to be working on in class to apply this idea of leverage.